Hello, today we're going to be solving LeetCode problem 438. Find all anagrams in a string. Given two strings, S and P, return an array of all the start indices of P's, anagrams in S. You may return the answer in any order. And then they have a description of what an anagram is. So an anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. We have two examples here. Let's start by looking at example 2. So the input S is ABAB, string P is AB, and the expected output is 0, 1, and 2 because at starting index 0 we have AB, which is a anagram of AB, and then at index 1 BA is an anagram of AB again, and starting index 2 AB is another anagram of AB. Example 1, we have index 0 because CBA is an anagram of ABC, and at index 6, BAC is an anagram of ABC, and no other starting indices form a anagram of ABC. Regarding the constraints, S and P are both non-empty strings, so at least one character, and S and P consist of lowercase English letters, any of the 26 characters in the English alphabet. So the first thing we have to decide is how we're going to check if a string is an anagram of another string. So for this, we could just check if the two strings have the same set of characters and the same number of instances of each character. We can use a hash map to represent the string as a character to count map. So for a given string, we can iterate through all of its characters and create a map mapping from its character to the number of instances that the character appears in the string. So for example, ABAC would map to A pointing to 2, B pointing to 1, and C pointing to 1. And if two strings have the same map representation, like these two, then they are anagrams of each other. So we can start off by implementing our helper class that will map from character to the number of instances that appears in the string. I define this function called getCharacterCountMap. As mentioned before, we'll be creating a Python dictionary, and we will iterate through all the characters in the input string S. For each character, we will increase its count in dictionary D. And then we can return the populated dictionary. So now that we know how to check if two strings are anagrams of each other, we can go back to the original problem. So let's use the following strings S and P for a running example. So we need to find all substrings in S. They're an anagram to P, and return the starting indices of each of those substrings. And we know that we're going to be using the map representations to check if the strings are an anagram of each other. So we can start by getting the map representation of P. We can check all substrings in S and check if they're an anagram of P. Since anagrams always have the same number of characters as the original string, we can simplify by only checking the substrings of S of length equal to the length of P, which in this case is 3. So we can iterate through S and check the substrings of length 3 and check if they are anagrams of P. We can start at index 0. So for each starting index, we generate the map representation of the substring. So in this case, the substring is going to be CBA. And if the substring representation is equal to P's representation, we found an anagram, and we want to add the starting index to the result list. The substring character to count map is equal to P's character count map. So that means they are an anagram of each other because the map representations are the same. And we then want to add the starting index 0 to the result list. We continue this process down the string, going through all possible starting indices until we no longer have a remaining substring of length 3. We go to index 1. Notice that for each iteration, we disregard the previous character to count map and we create a new one. And throughout the iterations, we check if the map is equal to the P's character to count map. And if they are, we add them to the result list. So the current solution works, but we can do better. So right now, we are creating our map representation for every substring of length S and P. So our big O is polynomial complexity. So it would be S minus P times P, where S is the length of string S and P is the length of string P. For the outer loop, we iterate through all start indices. That would be S minus P because we just want to go over the start indices of the substrings with length equal to the length of P. And inside each iteration, we're recreating the map representation, which is of type complexity O of P. And then comparing is constant time because for each map representation, there can be at most 26 different keys, one key for each character in the English alphabet. So we can improve the type complexity of the solution by using the sliding window technique. So the goal of the sliding window technique is to reduce nested loops. The idea is that we don't need to recreate the map representation of the substring during each iteration. So for each iteration, the map representation only changes by 2 characters. So the character that is no longer in the substring is removed from the map, and the character that is now part of the substring is introduced to the map. So going back to our example, so if we are at index 0, we have this map representation. And if we move to the next iteration, index 1, C is no longer part of the substring, so we remove from the map representation. And now D is part of the substring, and we introduce it to the map representation. So during each iteration, we no longer have to recreate the map from the start, which is of time complexity O of P. So now the time complexity of the sliding window technique is reduced to linear complexity. So capital S is the length of the string S, capital P is the length of string P. We start by creating the map representation of time complexity O of P, and then for each iteration, we go through all starting indices. So that's going to be of time complexity S minus P. During each iteration, we are going to be adjusting the map representation with the new window. So we're going to remove the old character and introduce a new character that is of constant time complexity. And then again, comparing the representations is constant time because there can be at most 26 different keys. So now we can start implementing our solution using the sliding window technique. So we have inputs S and P. We want to find all substrings in S or an anagram of P. Because of that, we know that if P has a length greater than the length of S, we can just return early because it's impossible to form any anagrams. Then we can create the P character map representation using our helper function. We're going to define our first starting index. We're going to start at 0. And then we can define our window. The window will start at the starting index, and it will be of length of P. And then we can start by getting the map representation of the window. And then we want to keep track of the results found so far. So for that, we can just create a list. Next, we can start our loop. For that, we can just use a while true loop. First, we can check if the current window is a anagram to P. For that, we just compare the two map representations. If they are equal, we just append the start index to our result list. Next, after checking the current window, we have to move the window right. So for that, we are going to remove the character that is no longer part of the window from the map representation. We have to check if the character is the only character in the map representation so far. In that case, we just want to remove the whole key from the dictionary. Otherwise, we just decrement its count by 1. We want to move the start index forward, and from there we're going to get a new character that will be part of the window. For that new character, we want to introduce it to the character map representation. Notice that if the new start index is out of range, then we can break from the loop and return the result. So the new character index will be at the start index plus the length of string p minus 1. And if the new character index is out of bounds of string s, then we can break from the while loop. If it's not out of bounds, then we want to add the new character to the map representation. And finally, outside of the while loop, we can just return result list. There are a couple of things that you can watch out for to identify if a problem can be solved using the sliding window technique or not. The most important characteristic is that you are dealing with sequential data. So for example, a string or array. On top of that, another signal is that the problem is asking to find a contiguous section that matches a specific target. For example, finding a substring that is an anagram of another string. One more indicator is that the naive solution has some form of iterative pattern with a nested loop to find the target. For the problem we solved in this video, we iterated through all possible starting indices, and for each iteration we constructed the map representation, which by itself was another loop. Of course, not every problem that follows this pattern guarantees a sliding window solution, but it is still an important tool to consider when solving problems of this type.